Professor Civil Engineering IT Madras to deliver a note on design of durable concrete across different strength grades with fly ash and slag. Sir, request you to kindly keep your presentation limited to 20 minutes, please. Thank you.
Can we have the presentation? Okay. Yeah, so very good afternoon to all of you. In the interest of time, I think I'll keep this as short as possible, but I just wanted to convey some specific messages with the help of this presentation. I hope that will come out clearly. So thanks to the organizing committee for bringing me here, and it's a good chance for me to interact with all of you, especially coming to hear about things that as concrete technologists we don't really deal with that much, trying to understand the complexities there are in utilization of these materials and getting them to be process ready to be actually used in concrete. But here I'm going to present something which I am more comfortable with, use of fly ash and slag, which has been done for decades, but we still don't see the kind of applications that we want to see in the future. So I'm just going to give you some glimpse of what these materials are capable of doing and how we have shown through research at IIT Madras the extent of improvement and durability that you can actually achieve with concretes at different strength grades. Of course, this is something that most of you are familiar with, the sustainability triple bottom line. And for a process to be sustainable, of course, it needs to be satisfying all three. The previous speaker also mentioned that if something is not economically sustainable, it cannot be environmentally sustainable. Makes perfect sense. Any process has to be looked at from the perspective of all of these aspects. Now, the issue is, the question which we have to often define is what is sustainable and for whom. To some people, bad concrete may be sustainable, right? Because they get to make the same structure over and over again. They keep doing repairs. A lot of business is generated, work, everybody's happy, right? But that's not what we want. What we generally have a consensus on with respect to sustainability in concrete construction is that something that emits lower CO2, something that has lower embodied energy overall, and something which has a prolonged life. So we want our concrete, which has been generated by using all these cementitious materials, to have a prolonged life and ensure that we also emit low CO2 and energy in the long run. Of course, there is no one solution with which you can actually get all of these incorporated in concrete. So there are global solutions and there are local solutions. Out of global solutions, we all know that when cement is manufactured, you have limestone in the cement mines. And limestone usage globally has been recognized as one of the ways to cut down the extent of CO2 emissions coming from cement manufacture. So Portland limestone cement is one of the examples of when people are using limestone as a partial replacement of cement. On the other hand, you have local solutions. For instance, fly ash, although it's available worldwide, is more of a local solution because if you don't use it in the vicinity of where fly ash is generated with thermal power plants, sometimes the transportation becomes a factor and you can't really use it directly in concrete. But of course, you can still use it as a blended cement. So just to give you a background on concrete performance, you know that a lot of concrete is used in the world. We need these major properties from concrete, that is workability, compressive strength, durability, and dimensional stability. And it turns out that the first three depend a lot on the way that cement interacts with water, or in other words, depends on cement chemistry. And the last one, dimensional stability, depends on the fact that we pack the material well enough with these inert materials, which are aggregates, and minimize the use of cement paste. If you really think about it, most of the reactions in the concrete in the long run where concrete is subjected to durability issues is because of the instability of the cement paste in various different environments. Aggregates, for the most part, are inert, and we want more of them to ensure that the concrete becomes dimensionally stable. So just to give some details of cement chemistry, many of you may be aware of this already, that we have a primary binding phase, which is calcium silicate hydrate. We also produce calcium hydroxide and cement hydration, and we produce secondary products like calcium sulfoaluminates, which are responsible for some setting and other properties within the concrete. So just to give you, as hydration happens, the porosity in the cement paste gets filled, or if you think about concrete, the pores in the concrete keep getting filled with time, and as a result, you have lesser porosity finally in the hardened product, and much of these pores remain disconnected, which leads to the durability. So Now, in concrete, the complication is because we have aggregate along with paste. So there are interfaces between aggregate and paste, which are much higher, which have much higher porosity than the paste itself. So a very important aspect would be to ensure that we choose cementitious systems where these interfaces can be properly filled up. So we also get calcium hydroxide. It has a complicated nature. It's absolutely important for concrete to have calcium hydroxide, but at the same time, when you have a chemical attack like chloride or a sulfate, calcium hydroxide is the first one to start reacting. And there is, as I said, inefficient filling of void spaces in the concrete that leads to an improper assessment of the porosity in the system. So if we start using these mineral additives or supplementary materials, we can tackle both of these issues at once. We convert calcium hydroxide to calcium silicate hydrate, increase the binding capability of the concrete. At the same time, we ensure that we optimize grain size of the use of these materials to ensure that our interfaces have been filled up properly. So these are major benefits of SCMs. Fly ash and slag obviously are two of the SCMs that are most commonly used. So just to answer this question in a slightly different fashion, how much cement do we need in concrete? Okay, so we make concrete of different strength grades, but how much cement do we actually need for the concrete to work? Theoretically, if you look at all kinds of calculations, about a water to cement ratio of 0.42 is required for complete hydration of cement, 100% hydration. But do we really need 100% hydration is the question? And in reality, a large chunk of the cement remains unhydrated for years. If you take, this is, somebody said 102-year-old building, if you take some concrete chunks from this building, you'll find that there is still a lot of cement which is not hydrated. It's simply not physically possible for water to find its way to each and every particle of cement in the concrete. So what does this mean? A lot of cement is not being utilized in the concrete. So why not fill it up with something else? So cement also has a filler role apart from the role of a hydration or hydration product. So filler can be easily a supplementary cementing material. Why do we need to waste our money to put in more and more cement? And of course, we know that using cement obviously increases the CO2 emission. So let's try to cut down that by using more of these supplementary materials. So of course, supplementary materials have an impact on all the three aspects. Environmentally, we are using waste or byproducts, okay? And we are reducing cement clinker usage that cuts down the CO2 emissions, which of course the figures can be differing from different presentations. More or less people agree that around 6 to 8% of CO2 emissions is because of the production of cement clinker, right? And then you have social impact. When you do use these supplementary materials, you get long-term durability, you get resistance to cracking in most of these cases because the thermal load of the concrete comes down as a result of the slower hydration process. And of course, as far as the long-term durability is concerned, most durability phenomena are positively affected. I'll show you some results later just to capture this in a much better form. So you get an increased benefit to cost ratio and a longer service life. So obviously, you also have an economic advantage to the use of these mineral additives. Okay, again, the primary reaction we are looking at with these mineral additives is the reaction of the amorphous silica that is there in your fly ash, or the kind of reactive structure that is there in your slag, and its consumption in a reaction that leads to the formation of additional CSH. So just to give you a range of compositions that you can expect from these materials, if you look at your slag, which is basically lime-rich, okay, I don't think the pointer will work. The slag is in a position which is slightly above Portland cement in terms of its equality of calcium and silica in the slag, whereas fly ash is more of an aluminosilicate. It does not really have that much of calcium in it. Some type C fly ashes are available, but they have a very different chemistry. Right, so if you can look at the binders overall, you can break them into three types. You have a hydraulic cement, which reacts with water without any activation. There is excess of calcium in the system. So basically, these are the hydraulic cements, or OPC, ordinary Portland cement belongs to this category, obviously. Then you have the latent hydraulic materials, which have a deficiency of calcium. So hydration basically has to happen by activation. So either you can do an activation using alkalis or sulfates. When you mix slag with cement, the activation is because of both alkalis and sulfates. And then, of course, you have the pozzolanic systems, which cannot react with water directly. They react with lime or calcium hydroxide in the presence of water. And here you have a severe deficiency of calcium, because of which you don't really have this sustaining reaction on its own, right? So again, slag belongs to the latent hydraulic, whereas fly ash belongs to the pozzolanic set of materials. Okay, So moving forward, of course, I don't have to go through this. You are in the place where steel is manufactured and slag is available in large quantities. So this is basically your granulated blast furnace slag. There are other types of slags. A lot of it has been discussed. Steel slags like LD slag, people have talked about how these can be used as partial replacements. There's been a study also done by NCB along with Tata Steel, which shows that yes, indeed, this is possible. There are ferromanganese slags and copper slags. Many of these are not suitable for cement making because of chemistry not being favorable. And mineralogy also sometimes is difficult to actually route in the form of making cement. There's also other processes of slag manufacture or slag production like Corex process, which produces a slightly different type of slag, which is quite reactive in terms of its reactivity with the cement. Right, so what are the properties of slag? Of course, I'm talking primarily about blast furnace slag. I'm not really focusing too much on other steel slags. So here, these are some of the physical properties. And what we do is we utilize slag at a very high level of replacement of the cement, nearly 40 to 60%. In fact, in most cases, when we have Portland slag cement, we are in the range of about 50%, although increasingly people have started moving towards higher replacement levels, more than 60% even is seen. Up to 70% is of course permitted as far as Portland slag cement is concerned. Of course, fly ash is collected in thermal power plants. As very clearly you saw in the previous presentations, about 70 to 80% of the ash basically is flying out and is collected in electrostatic precipitators. And a lot of the fly ashes which are not suitable for use in cement manufacture are getting dumped as slurry in the ponds. And depending on the collection field, sometimes the kind of characteristic particle sizes and the compositions of the fly ash that you get could be quite different. So if you are actually collecting it for direct ready-mix concrete production, there is a high chance that you'll get a lot of variability in the fly ash. That is one aspect that has not been resolved yet. When fly ash is not available in the form of blended cement, if people want to use it in concrete and RMCs, they still have a lot of challenges because of the high variability that you get with fly ashes. So that is something one needs to be. So there may be a need for processing when you want to directly use it in concrete. Indeed, today processed fly ashes are available, but of course, processing involves costs. So that increases the cost of your fly ash availability in the concrete. But I don't see the harm in doing that. Many Western countries do that. They process fly ash and ensure that fly ash can be used as a commodity product like cement. So fly ashes, of course, depending upon their source, they can be high calcium or low calcium. More or less, the particle sizes are similar. It's not that much different. And in terms of the particles, we know that they have a spherical nature. There are processing can help actually extract a lot of these superfines and also the sphenospheres that can lead to very different value-added applications in the construction industry. Okay, so again, fly ash is typically used in the form of blended cement, and the fly ash typically is about 25 to 30%. Up to 35 is permitted, but most commercial products do come up with 25 to 30%. RMC, again, up to 35% can be used, but typical replacement levels, at least what I have seen, are around 20 to 25%. High volume fly ash is definitely possible, but you definitely need a highly extended curing. Many people in the sites are not very ready to do that actually. Unfortunately, this forum has everybody that believes that fly ash and slag should be used, but we also have to think about the vast majority of the structural designers who don't really permit these alternative materials. Am I short on time? Sure. I'll speed up. So, because a lot of the results will follow based on what I'm going to say here. So, with slag and fly ash, we expect that the speed of hydration and strength gain will be slower in the beginning, but then in the long run, you can expect that with adequate curing, you are going to get a microstructure that is much better evolved as compared to plain Portland cement, resulting in very high durability. And why I wanted to emphasize that is that we generally associate durability with higher strength achieved in the concrete. But I'm going to show you results where it is clear that even for concrete produced for normal applications, M25, M30 concretes, which are not expected to be highly durable, you can incorporate these materials and get much higher durabilities. So let's just go into the results. I mean, of course, we had done durability mechanisms covering a range of mechanisms, and also the test methods that we chose for this encompassed a wide variety of test methods. So I'll not describe these test methods, but I just wanted to give you a snapshot of what was used: gas penetrability, water permeability, and concrete resistivity, and also chloride-related tests were actually assessed. We looked at various mix designs to cover a gamut of applications that have been used in ready-mix concrete. Water binder ratios were also varying significantly, and we used different types of fly ashes and slag. So here you can clearly see the surface resistivity of the concrete, which is produced by increasing replacement of cement with fly ashes and slag, continues to increase. Now, why is that a good thing? The higher the surface resistivity, the lower is the connectedness of the porosity. So if the pores are connected, you'll get more conductivity. If the pores are disconnected, you get higher resistivity. So if you get a higher resistivity, indicates better durability. And of course, as you can expect, with most of the pozzolanic systems or slag-related systems, the higher level of curing increases that even further. But nevertheless, you can see the kind of increase that you get for 50% slag and for the 50% fly ash mixes, much higher as compared to Portland cement. Okay, these are individually showing the same results. That previous one was actually a combined result of all of those together. And this is for a very moderate grade of concrete, 310 kilograms of binder and 0.5 water to binder ratio. So it's a very moderate M30 type concrete, okay? So again, so with fly ash type C, which is more cementitious, you don't really see that much of an enhancement in the resistivity as compared to your plain Portland cement. Now, as far as chloride penetrability is concerned, I've plotted it across the range of binder contents and all the water binder ratios, and you can see very clearly that the RCPT result, which is shown on the right slide, is clearly indicating that as you're increasing the SCM replacement level, irrespective of what supplementary material you're using, you are seeing a major reduction in the chloride penetrability. Now, you may ask, okay, even with a 0% replacement with a Portland cement, I'm still able to get around 1,000 coulombs. But why is that? Because that is with a high binder content and low water binder ratio. That means a higher grade concrete. But what is happening here at the level of 50% replacement is that you are at 310 binder and 0.5 water binder ratio. What does this tell you? This tells you that even in ordinary grade concretes of M20 to M30, we can achieve significantly good durability with the use of supplementary materials at high replacement levels. Much of our applications are basically of these 20 to 30 grade concretes. But you see very routinely, you see people on site using M20 grade concrete with 400 kilograms of cement because they don't want to use chemical admixtures, they want to use enough water. So 400 kilograms of cement for an M20 grade concrete. Absolute waste, a criminal activity, it needs to be stopped. Right? We really need to ensure that such concretes see a large replacement with cementitious replacement materials like fly ash and slag. So again, I'll not go into the details of this. Of course, you'll have this presentation available in case you want it. These are more of the details as to why this happens. There's a lot of chloride binding, which we were able to show by scanning electron microscopy, trying to understand where the chloride goes into the structure of the cementitious materials. And there's, of course, tons of international literature available also. Similar results with water sorptivity, which indicate that much lesser water penetration also happens inside these admixed systems. So I've just also captured here what are the real characteristics that are required in different durability problems like sulfate and other chemical attack. The primary aspect is a lower permeability, and that you can really achieve very well with mineral admixtures. Chloride-induced corrosion, low permeability is very helpful. At the same time, you also need chloride binding, and that's where your alumina from the slag and fly ash really plays a large role in helping in the chloride binding. One problem often stated by people who don't want to use mineral admixtures is carbonation. Yes, carbonation is going to be higher because a cement that is low in terms of embodied CO2 will have definitely a greater CO2 uptake capacity. So that means there'll be more carbonation happening through blended cements. However, you can design against that. You know what are the rates at which carbon dioxide penetration will take place. You can design appropriately by choosing the right cover and the right densification that happens with the use of mineral additives. So anyway, alkali-silica reaction, any blended cement will perform much better. Even if you have alkali reactive aggregates, fly ash and slag-based cements are definitely going to give you superb results. Okay, so some myths and realities. SCMs cannot be used when early strengths are desired. Many people don't want to use fly ash, for instance, in pre-stress concrete because they are expecting the early strengths to be compromised. So that's a myth. Another myth is SCMs cannot be used in precast construction, and since strength development is low, durability is also negatively affected. These are some of the thoughts that structural designers have. In reality, of course, if the concrete that needs to be designed for early strength, you can really get early strengths even with cementitious replacement materials. SCMs respond very well to seam curing. So in precast products, you can really get excellent performance with fly ash and slag. Oops, sorry. And then finally, there's definitely no reason to believe that high strength is high durability. I'll show you this is the kind of pattern that we get if you plot strength and durability parameters when you have more than one type of binder in your system. So please realize that you need to test for durability and assess it. There's no clear relationship between strength and durability. In the old days, we were only using OPC. So when we reduce water cement ratio, strength goes up, durability also goes up. But here, we are talking about high durability even with moderate to high water cement ratios when we use fly ash and slag. Okay, just to summarize, supplementary materials are absolutely essential. Fly ash and slag primarily, of course, they increase cost effectiveness and reduce environmental impact of concrete. And since today we are talking about what can we do in terms of policy decisions to make things happen positively, use of plain Portland cement should not be permitted for any construction activity. One has to be able to use Portland cement in combination with mineral additives or blended cements, as the case may be, if you really want to make a big difference. Earlier, somebody had said, okay, the government mandates that 5% of your material has to be recycled, then obviously everybody will start following and coming in line. This is another such initiative. Okay, thank you all. I'll stop with this.
Thank you so much, sir. The presentation was really very interesting.
Thank you.
I request Dr. Sanjay to please hand over the token of appreciation.
Nice project.